Alright, welcome back everybody. In this video we're going to start the examples from the Introduction to Optimization lesson. When we talk about optimization, we're trying to find an optimal value for something, either a maximum or a minimum, depending on the context. And we typically use this 6-step process. First, make sure you understand the problem, read through the problem, etc. Second, we want to develop a mathematical model of the problem, draw pictures if it's appropriate, and label important parts. If it's not appropriate to draw a picture, don't try and draw a picture. Figure out a variable to represent the quantity that needs to be optimized. Use that variable to write a function whose extreme value will give us the information that we seek. Make sure you consider the domain of the function. What values of the variable make sense in the context of the problem, which is going to help us to identify critical points and endpoints. We want to find the critical points and endpoints, and then use a sign chart to make sure that the point you find meets the criteria of your problem. You want to find the value of the function for the appropriate critical points, and then interpret your solution. Make sure that your solution makes sense in the given context. Alright, so let's look at example 1. An open top box is to be made by cutting congruent squares of side length x from the corners of a 30 by 45 inch sheet of cardboard and bending up the sides. How large should the squares be to make a box of maximum volume? So we've got a box, or a sheet of cardboard rather. My sheet of cardboard is green with a purple border. And this is a 30 by 45 sheet of cardboard. And what we're doing is we're cutting squares out of the corners of some unknown length. And so our variable in our model here is going to be x. Now if we cut out those same size square corners and fold along the dotted lines here, we will have an open-topped box. Alright, so now we want to develop our model, and we're trying to find how large the square should be to make a box of maximum volume, and what is the resulting maximum volume. So we want to write a function for the volume of this box. And the volume of the box, since it's a three-dimensional cube, open cube, the volume is going to be the length times the width times the height. And so we have 3 dimensions here. The folded up side is 1 dimension. And then these distances here are the length and the width of the box. And so one of those is 30 minus 2x, and the other one is 45 minus 2x. Now consider our domain for these values. What are the realistic values for x? It has to be bigger than 0, because if you don't cut out any side length square, you're not going to have anything to fold up to make the box. And it has to be less than 15, because if we cut a box that's 15 units on each side, we'll cut the entire side dimension away, and again we'll be left with a flat sheet of cardboard where we don't have anything to fold up. So that's our realistic domain. Alright. Now we want to identify the critical points and the endpoints of the function. In order to do that, I'm going to simplify this. Let's see, that's 1350 minus 60x minus 90x plus 4x squared. And distributing the x through and combining like terms, we end up with this expression for the volume, 4x to the third minus 150x squared plus 1350x. And we want to find the critical points of this function. So we take the derivative. It's 12x squared minus 300x plus 1350. And now we want to find our potential critical points. So I'm going to solve this function, set it equal to 0, and solve. And so let's see, y equals 12x squared minus 300x plus 1350, and realize our realistic domain was only from 0 to 15, so that's where I'm going to look for critical points. and we have 1. So we want to calculate the value of that 0. There you are, cursor. And we find x equals 5.885 6217. And now I'm going to make a sign chart for v prime. Analyze what's going on. It goes from 0 to 15, and we've got 5.886, where the derivative is 0. And now we want to look at positive negativity of this. If I substitute 1 into the original volume function, I get a positive value. And if I substitute 10 into the original volume, or pardon me, into the derivative, I get a negative value. And so this x value produces a maximum, which is exactly what we want. And so now we need to answer our question. The squares should be 5.886 inches by 5.886 inches. And the resulting maximum volume, let me just say max volume instead of putting v equals. And we want to put 5.886 into our volume function, so we've got 5.886. Let's keep more decimal places of it. 6217 times quantity 30 minus 2 times 5.8856217 times 45 minus 2 times 5.88617. Uh-oh, what did I do? I forgot a parenthesis. And we get that the max volume is 3,564. 3,564.905 cubic inches. And we've answered our question. Alright, that's the end of example 1. We'll come back next time and look at example 2.